travels in space and time. The rising and falling of the surf is produced in part by tides. The moon and the sun are far away, but their gravitational influence is very real and noticeable back here on Earth. The beach reminds us of space. Fine sand grains, all more or less uniform in size, have been produced from larger rocks through ages of jostling and rubbing, abrasion and erosion. Again driven through waves and weather by the distant moon and sun. And the beach also reminds us of a time. The world is much older than the human species. A handful of sand contains about 10,000 grains, more than the number of stars we can see with the naked eye on a clear night. But the number of stars we can see is only the tiniest fraction of the number of stars there are. What we see at night is the merest smattering of the nearest stars. Meanwhile, the cosmos is rich beyond measure. The total number of stars in the universe is greater than all the grains of sand and all beaches of planet Earth. Despite the effort of ancient astronomers and astrologers to put pictures in the skies, a constellation is nothing more than an arbitrary grouping of stars, composed of intrinsically dim stars that seem to us bright because they are nearby, and intrinsically brighter stars that are somewhat more distant. All places on Earth are to high precision the same distance from any star. This is why the star patterns in a given constellation do not change as we go from, say, Soviet Central Asia to the American Midwest. Astronomically, USSR and the United States are the same place. The stars in any constellation are so far away that we cannot recognize them as the three-dimensional configuration as long as we are tied on Earth. The average distance between the stars is a few light years. A light year being, remember, about 10 trillion kilometers. For the patterns of the constellation to change, we must travel over distances comparable to those what separate the stars. We must venture across the light years. Then some nearby stars will seem to move out the constellation. Otherwise, then others will enter it, and its configuration will alter dramatically. Our technology is so far utterly incapable of such grand interstellar voyages, at least in reasonable transit times. But our computers can be taught that three-dimensional positions of all nearby stars. We can ask to be taken on a little trip, or circumnavigate on a collection of bright stars that can constitute the Big Dipper, say, and what constellation change. We connect the stars in typical constellations. In the usual celestial follow the dot drawings. As we change our perspective, we see their apparent shapes distort severely. The inhabitants of the planet of distant stars witness quite different constellations in their night skies than we do in ours. Other Rorschach tests for other minds. Perhaps sometimes in the next few centuries, a spaceship from Earth would actually travel such distance at some remarkable speed and see new constellations that no human has ever viewed before, except with such a computer. The appearance of the constellations changes not only in space but also in time. Not only if we are alter our position, but also if we merely wait sufficiently long. Sometimes stars move together in a group or a cluster. Other times, a single star may move very rapidly with respect to its fellows. Eventually, such stars have an old constellation and enter new one. Occasionally, one member of a double star system explodes, breaking the gravitational shackles that bound its companion, which then leaps into space at its former orbital velocity. A slingshot in the sky. In addition, stars are born, stars evolve, and stars die. If you wait long enough, new stars appear and old stars vanish. The patterns in the sky slowly melt and alter. Even over the lifetime of the human species, a few million years, constellations have been changing. Consider the present configuration, the Big Dipper, or Great Bear. Our computer can carry us in time as well as in space. As we run the Big Dipper backward into the past, allowing for the motion of its stars, we find quite a different appearance million years ago. The Big Dipper then looked like a spear. If a time machine dropped you precipitously in some unknown age in the distant past, you could in principle determine the epoch by the configuration of the stars. If the Big Dipper is a spear, this must be Middle Pleistocene. We can also ask computer to run constellation forward into time. Consider Leo the Lion. The zodiac is a band of 12 constellations seemingly wrapped around the sky in the apparent annual path of the sun through the heavens. The root of the word is that for zoo, because the zodiacal constellations, like Leo, are mainly fancied to be animals. A million years from now, Leo will look still less like a lion than it does today. Perhaps our remote descendants will call it the constellation of the radio telescope. Although I suspect a million years from now, the radio telescope will have become more obsolete than the stone spear is now. The non-zodiacal constellation of Orion, the Hunter, is outlined by 4 bright stars in a bisected by a diagonal line, 3 stars, which represent the belt of the Hunter. 3 dimmer stars hanging from the belt are, according to the conventional astronomical project test, Orion's sword. The middle star in the sword is not actually a star, but a great cloud of gas called Orion Nebula, in which stars are being born. Many of the stars in Orion are hot and young, evolving rapidly and ending their lives in colossal cosmic explosion called supernova. They are born, die in periods tens of millions of years. If on our computer we were to run Orion rapidly into far future, we will see a startling effect. The bursts spectacular deaths, many of its stars, flashing on, winking off like fireflies in the night. The solar neighborhood, the immediate environs of the sun in space, includes the nearest star system, Alpha Centauri. It is really a triple system, 2 stars evolving around each other, and a third, Proxima Centauri, orbiting the pair at a discrete distance. At some positions on its orbit, Proxima is the closest known star to the sun, hence its name. Most stars in the sky are members of double or multiple star systems. Our solitary sun is something of an anomaly. The second brightest star in the constellation Andromeda, called Beta Andromeda, is 75 light years away. The light by which we see it now has spent 75 years traversing the dark of interstellar space on its long journey to Earth. In the unlikely event that Beta Andromeda blew itself up Tuesday, we will know it for another 75 years. As this interesting information, traveling at the speed of light would require 75 years to cross the enormous interstellar distances. When the light by which we now see this star set out on its long voyage, the young Albert Einstein, working as a Swiss patent clique, had just published his epochal special theory of relativity here on Earth. Space and time are interwoven. We cannot look out into space without looking back in time. Light travels very fast, but space is very empty, and the stars are far apart. Distances of 75 light years or less are very small compared to other distances in astronomy. From the Sun to the center of the Milky Way galaxy is 30,000 light years. From our galaxy to the nearest spiral galaxy, M31, also in the constellation Andromeda, is 2 million light years. When the light we see today from M31 left for Earth, there were no humans on our planet, although our ancestors were evolving rapidly to our present form. The distance from the Earth to the most remote quasars is 8 or 10 billion light years. We see them today as they were before the Earth accumulated, before the Milky Way was formed. This is not a situation restricted to astronomical objects, but only astronomical objects are so far away that the finite speed of light becomes important. If you are looking at a friend 3 meters or 10 feet away, at the other end of the room, you are not seeing her or she is now, but rather as she was 100 millions of a second ago. 3 meters divided by 3 times 10 to 8 power meter per second, which is 10 divided by 10 to 8 power second, or hundredths of microsecond. In this calculation, we have merely divided the distance by the speed of the get travel time, but the difference between your friend now and now minus 100 millions of a second is too small to notice. On the other hand, when we look at quasar 8 billion light years away, the fact we are seeing it as 8 billion years ago may be very important. For example, there are those who think that quasars are explosive events likely to happen only in the early history of galaxies. In that case, the more distant the galaxy, the earlier in its history we are observing it, and the more likely it is that we should see it as a quasar. Indeed, the number of quasars increases as we look into a distance of more than 5 billion light years. The 2 Voyager interstellar spacecraft, the fastest machines ever launched from Earth, are now traveling at 10,000 the speed of light. They would need 40 million years to go the distance the nearest star. Do we have any hope of leaving Earth and traversing the immense distance even to Proxima Centauri in a convenient period of time? Can we do something to approach the speed of light? What is magic about the speed of light? Might we someday be able to faster than that? If you had walked through the present Tuscan countryside in the 1890s, you might have come upon somewhat long-haired teenage high school dropout on the road to Pavia. His teachers in Germany had told him that he would never amount to anything, that his question destroyed classroom discipline. He would be better off out of school. So he left and wandered, delighting in the freedom of northern Italy, where he could ruminate on matters remote from the subject he had been force-fed in his highly disciplined Prussian schoolroom. His name was Albert Einstein. His rumination changed the world. Einstein had been fascinated by Bernstein's People's Book of Natural Science, a popularization of science that described on its very first page the astonishing speed of electricity through wires and light through space. He wondered what the world would look like if you could travel on a wave of light, to travel at the speed of light. What an engaging and magical thought for a boy on the road in the countryside, dappled and rippling in sunlight. You could not tell you were on a light wave if you travel with it. If you start on the wave crest, you would stay on the crest and lose all of the light. Notion of being a wave. Something strange happens at the speed of light. The more Einstein thought about the questions, the more troubling they became. Paradoxes seemed to emerge everywhere if you could travel at the speed of light. Certain ideas had been accepted as true without sufficiently careful thought. Einstein posed simple questions that could have been asked centuries earlier. For example, what do we mean we say the two events are simultaneous? Imagine that I am riding a bicycle toward you. As I approach an intersection I nearly collide. So it seems to me, with a horse-drawn cart, and I swear, I'll swerve and barely avoid being run over. Now think of the event again, and imagine that the cart and the bicycle are both traveling close to the speed of light. If you are standing down the road, the cart is traveling at right angles to your line of sight. You see me, by reflected sunlight, traveling toward you. Would not my speed be added to the speed of light, so that my image would get to you considerably before the image of the cart? Should you not see sweep before you see the cart arrive? Can the cart approach intersection simultaneously from my point of view, but not from yours? Could I experience a near collision with the cart while you perhaps see me sweep around nothing and pedal cheerfully on toward the town of Vinci? These are curious and subtle questions. They challenge the obvious. There is a reason that no one thought to them before Einstein. From such elementary questions, Einstein produced fundamental rethinking of the world, a revolution in physics. If the world is to be understood, if we are to avoid such logical paradoxes when traveling at high speeds, there are some rules, commandments of nature, that must be obeyed. Einstein codified these rules in special theory of relativity. Light, reflected or emitted from an object, travels at the same velocity whether the object is moving or stationary. Thou shalt not add speed to the speed of light. Also, no material object may move faster than light. Thou shalt not travel at or beyond the speed of light. Nothing in physics prevents you from traveling at close to the speed of light as you like. 99.9% of the speed of light will be just fine. But no matter how hard you try, you can never gain that last decimal point. For the world to be logically consistent, there must be a cosmic speed limit. Otherwise, you could get to any speed you wanted by adding velocities on a moving platform. Europeans around the turn of the century generally believed in privileged frames of reference, that German, French, or British culture and political organization were better than those of other countries. The Europeans were superior to other peoples who were fortunate enough to be colonized. The social and political application of the ideas of Aristotles and Copernicus was rejected or ignored. The young Einstein rebelled against the notion, privileged frames of reference in physics as much as he did in politics. In a universe filled with stars rushing helter-skelter in all directions, there was no place that was at rest, no framework from which to view the universe that was superior to any other framework. This is what the word relativity means. The idea is very simple, despite its magical trappings. In viewing the universe, every place is as good as every other place. The laws of nature must be identical, no matter who is describing them. If it is to be true, it will be stunning. if there were something special about an insignificant location in the cosmos, then it follows that no one may travel faster than light. We hear the clack of a bullwhip because the tip is moving faster than the speed of sound, creating a shockwave, a small sonic boom. A thunderclap has a similar origin. It was once thought that airplanes could not travel faster than sound. Today, supersonic flight is commonplace, but the light barrier is different from sound barrier. It is not merely an engineering problem like the one the supersonic airplane solves. It is a fundamental law of nature, as basic as gravity, and there are no phenomena in our experience, like the crack of a bullwhip or the clap of a thunder for sound, to suggest the possibility traveling in a vacuum faster than light. On the contrary, there is an extremely wide range of experience with nuclear accelerators and atomic clocks, for example, in precise quantitative agreement with special relativity. The problem of simultaneously do not apply to the sound as they do to light, because sound is propagated through some material medium, usually air. The sound wave that reaches you when a friend is talking is the motion of molecules in the air. Light, however, travels in a vacuum. There are restrictions on how molecules of air can move, which do not apply to a vacuum. Light from the sun reaches us across the intervening empty space, but no matter how carefully we listen, we do not hear the crackle of sunspots or the thunder of the solar flares. It was once thought, in the days before relativity, the light did propagate through a special medium that permeated all the space, called the luminiferous aether. But the famous Michelson-Morley experiment demonstrated that such an aether does not exist. We sometimes hear of things that can travel faster than light. Something called the speed of thought is occasionally preferred. This is an exceptionally silly notion, especially since the speed of impulses through the nerves in our brains is about the same as the speed of donkey cart. The human beings have been clever enough to devise relativity shows that we think well. But I do not think we can boast about thinking fast. The electrical impulses in modern computers do, however, travel nearby at the speed of light. Special relativity, fully worked out by Einstein in his middle 20s, is supposed by every experiment performed to check it. Perhaps tomorrow someone will invent a theory consistent with everything else we know that circumvents paradoxes on such matters as simultaneity, avoids previous reference frames, and still permits travel faster than light. But I doubt it very much. Einstein's prohibition against traveling faster than light may clash with our common sense. But on this question, why should we trust common sense? Why should our experience at 10 kilometers an hour constrain the laws of nature at 300,000 kilometers per second? Relativity does not limit on what humans can ultimately do. Relativity does set the limits on what humans can ultimately do, but the universe is not required to be in perfect harmony with human ambition. Special relativity removes from our grasp one way of reaching the stars, the ship that can go faster than light. Tantalizingly, it suggests another and a quite unexpected method. Following George Gamow, let us imagine a place where speed of light is true value 300 kilometers per second, but something very modest, 40 kilometers per hour, say, and strictly enforced. There are no penalties for breaking laws of nature because there are no crimes. Nature is self-regulating and merely arranges things so that its prohibitions are impossible to transgress. Imagine that you are approaching the speed of light on a motor scooter. Relativity is rich in sentence beginning imagine. Einstein called such an exercise Gedanken experiment, thought experiment. As your speed increases, you begin to see around the corners of passing objects. While you are rigidly facing forward, things that are behind you appear within your forward field of vision. Close to the speed of light, from your point of view, the world looks very odd. Ultimately, everything is squeezed into a tiny circular window, which says, just ahead of you. Which stays just ahead of you. From the standpoint of a stationary observer, light reflected off you is reddened as you depart and you blued as you return. If you travel toward the observer at almost the speed of light, you will become enveloped in a airy chromatic radiance. Your usually invisible infrared emission will be shifted to the shorter visible wavelengths. You become compressed in the direction of motion, your mass increases, and time, as you experience it, slows down. A breathtaking consequence of traveling close to the speed of light, called time dilation. But from the standpoint of an observer moving with you, perhaps the scooter has a second seat, none of these effects occur. These peculiar and at first perplexing predictions of special relativity are true in the deepest sense that anything in science is true. They depend on your relative motion, but they are real, not optical illusions. They can be demonstrated by simple mathematics, mainly first-year algebra, and therefore understandable to any educated person. They are also consistent with many experiments. Very accurate clocks carried in airplane slows down a little compared to stationary clocks. Nuclear accelerators are designed to allow for the increase of mass with the increasing speed. If they were not designed in this way, accelerated particles would all smash into the walls of the apparatus, and there would be little to do in experimental nuclear physics. Speed is distance divided by time. Since near the velocity of light we cannot simply add speed as we are used to do things in a workaday world, the familiar notions of absolute space and absolute time, independent of your relative motion, must give away. That is why you shrink. That is the reason for the dilation. Traveling close to the speed of light, you would hardly age at all. But your friends and your relatives back home would be aging at the usual rate. When you returned from your relativistic journey, what a difference there would be between you and your friends. They having aged decades, say that you having aged hardly at all. Traveling close to the speed of light is a kind of elixir of life, because time slows down close to the speed of light. Special relativity provides us with a means of going to the stars, but it is possible in terms of practical engineering. Is it possible, practical engineering, travel close to the speed of light? Is a starship feasible? Tuscany was not only the cauldron of some of the thinking young Albert Einstein, it was also home of another great genius who lived 400 years earlier, Leonardo da Vinci, who delighted in climbing the Tuscan hills, viewing the ground from a great height, as if he were soaring like a bird. He drew the first aerial perspectives of landscapes, towns, and fortifications. Among Leonardo's many interesting accomplishments in painting, sculpture, anatomy, geology, natural history, military, and civil engineering. He had a great passion to devise a fabricate machine that could fly. He drew pictures, constructed models, built full-size prototypes, and not one of them worked. Not sufficiently powerful lightweight engine then existed. The design, however, were brilliant and encouraged engineers in future times. Leonardo himself was depressed by these failures, but it was hardly his fault. He was trapped in 15th century. A similar case occurred in 1939, when a group of engineers, calling themselves the British Interplanetary Society, designed a ship to take people to the moon, using 1939 technology. It was by no means identical to the design of Apollo's spacecraft, which accomplished exactly this mission 3 decades later, but it suggested a mission to the moon might one day be practically engineering possibility. Today we have preliminary designs for ships to take people to the stars. None of these spacecraft is imagined to leave the Earth directly. Rather, they are constructed in Earth orbit, from where they are launched on their long interstellar journeys. One of them was Project Orion, after the constellation. A reminder that the ship's ultimate objective was the stars. Orion was designed to utilize explosion of hydrogen bombs, nuclear weapons, against an inertial plate, each explosion providing a kind of vast nuclear motorboat in space. Orion seems entirely practical from an engineering point of view. By its very nature, it would have produced vast quantities of radioactive debris, but for conscientious mission profiles, only in the emptiness of interplanetary or interstellar space. Orion was under serious development in the United States until the signing of an international treaty that forbids the detonation of nuclear weapons in space. This seems to me a great pity. The Orion starship is the best use of nuclear weapons I can think of. Project Daedalus is a recent design, British Interplanetary Society. It assumes the existence of a nuclear fusion reactor, something much safer, as well as more efficient than existing fission power plants. If we do not have fusion reactors yet, but they are confidently expected in the few new decades. Orion and Daedalus might travel at 10% the speed of light, a trip to Alpha Centauri, 4.3 light years away, and would then take 43 years, less than a human lifetime. Such ships could not travel close enough to the speed of light for special relativistic time duration to become important. Such ships could not travel close enough to the speed of light for special relativistic time dilation to become important. Even with optimistic projections on the development of our technology, it does not seem likely Orion, Daedalus, or their ilk will be built before the middle of the 21st century. Although if we wished we could build Orion now. For voyages beyond the nearest stars, something else must be done. Perhaps Orion and Daedalus could be used as multi-generation ships, so those arriving at a planet of another star would be the remote descendants of those who had set out some centuries before. Or perhaps a safe means of hibernation for humans will be found, so that the space travelers could frozen and then reawakened centuries later. Those non-relativistic starships, enormously expensive as they would be, look relatively easy to design, build and use compared to starships that travel close to the speed of light. other star systems are accessible to the human species, but only after great effort. Fast interstellar space flight, with the ship velocity approaching the speed of light, is an objective not for 100 years, but for 1,000 or 10,000. But it is in principle possible. A kind of interstellar ramjet has been proposed by Earl W. Bussard, which scoops up the diffuse matter, mostly hydrogen atoms, that floats between the stars, accelerates into a fusion engine, and ejects it out the back. The hydrogen would be both as fuel and a reaction mass. But in deep space there is only about one atom in every 10 cubic centimeters, a volume the size of a grape. For the ramjet to work, it needs the frontal scoop hundreds of kilometers across. When the ship reaches relativistic velocities, the hydrogen atoms will be moving with respect to the spaceship at close to the speed of light. If adequate precautions are not taken, the spaceship and its passenger will be fried by these induced cosmic rays. One proposed solution used a laser to strip the electrons off the interstellar atoms and make them electrically charged while they are still some distance away, an extremely strong magnetic field to deflect the charged atoms into the scoop and away from the rest of the spacecraft. This is engineering on a scale so far unprecedented on Earth. We are talking of engines the size of small worlds. But let us spend a moment thinking about such a ship. The Earth gravitationally attracts us with a certain force, which, if we are falling, we experience as an acceleration. Were we to fall out of a tree, and many of our proud human ancestors must have been done so, we would plummet faster and faster, increasing our fall speed by 10 meters per second, or 32 feet per second, every second. This acceleration, which characterizes the force of gravity holding us to the Earth's surface, is called 1g. G for Earth's gravity. We are comfortable with accelerations of 1g. We have grown up with 1g. If we lived in an interstellar spacecraft that could accelerate at 1g, we would find ourselves in a perfectly natural environment. In fact, the equivalence between gravitational forces and the forces we would feel in accelerating spaceship is a major feature of Einstein's later general theory of relativity. With a continuous 1g acceleration, after 1 year in space, we would be traveling very close to the speed of light. 0.01 kilometer per square kilometer seconds times the 30 million second equals 3 times 30,000 kilometers per second. Suppose that such a spacecraft accelerates at 1g, approaching more and more closely to the speed of light until the midpoint of the journey, and then it turns around and decelerates at 1g until arriving at its destination. For most of the trip, velocity would be very close to the speed of light, and time would slow down enormously. A nearby mission object, a sun that may have planets, is Barnard's star. About 6 light years away, it could be reached in about 8 years, measured by clocks aboard the ship. The center of Milky Way in 21 years, M31, the Andromeda Galaxy in 28 years. Of course, people left behind on Earth will see things differently. Instead of 21 years to the center of the galaxy, they would measure an elapsed time of 30,000 years. When we got home, few of our friends would be left to greet us. In principle, such a journey mounting the decimal point ever closer to the speed of light would even permit us to circumnavigate the known universe in some 56 years ship time. We will return tens of billions of years in our future to find the Earth a charred cinder and the Sun dead. Relativistic spaceflight makes the universe accessible to advanced civilizations, but only to those who go out the journey. There seems to be no way for information to travel back to those who left behind any faster than the speed of light. The designs for Orion, Daedalus, and the Buzzard Ramjet are probably farther from the actual interstellar spacecraft we will one day build than Leonardo models are now from space supersonic transports. Where we do not destroy ourselves, I believe that we will one day venture to the stars. When our solar system is all explored, the planets of other stars will beckon. Space travel and time travel are connected. We can travel fast into space only by traveling fast into the future. But what of the past? Could we return to the past and change it? Could we make events turn out differently from what the history books assert? We travel slowly into the future all the time, at the rate of one day every day. With relativistic spaceflight, we could travel fast into the future. But many physicists believe the voyage into the past is impossible. Even if you had a device that could travel backward in time, they say, you would be unable to do anything that would make any difference. If you journeyed into the past and prevented your parents from meeting, then you would never be born, which is something of a contradiction, since you clearly exist, like the proof of the irrationality of root 2. Like the discussion of simultaneously in space special relativity. This is an argument in which the premise is challenged because the conclusion seems absurd. But other physicists propose two alternative history, two equally valid realities could exist side by side. The one you will know and the one in which you were never born. Perhaps time itself has many potential dimensions, despite the fact we are condemned to experience only one of them. Suppose you could go back into the past and change it, by persuading Queen Isabella not to support Christopher Columbus, for example. Then it is argued you would have set into motion different sequence of historical events, which those you left behind in our timeline would never know about. If that kind of time travel were possible, then every imaginable alternative history might in some sense really exist. History consists for the most part of a complex bundle of deeply interwoven threads, social, cultural, and economical forces that are not easily unraveled. The countless small, unpredictable, and random events that flow on continuously often have no long-range consequences, but those occurring at the critical junctures or branch points, may change the pattern of history. There may be cases where profound changes can be made by relatively trivial adjustments. The farther in the past such an event is, the more powerful may be its influence, because the longer the lever arm of time becomes. A poliovirus is a tiny microorganism. We encounter many of them every day, but only rarely, fortunately, does one of them infect one of us and cause this dread disease. Franklin D. Roosevelt, the 32nd President of the United States, had polio. Because the disease was crippling, it may have provided Roosevelt with a greater compassion for the underdog, or perhaps it improved his striving for success. If Roosevelt's personality had been different, or if he had never had the ambition to be President of the United States, the Great Depression of the 1930s, the World War II, and the development of nuclear weapons might just possibly have turned out differently. The future of the world might have been altered, but a virus is an insignificant thing, only a millions of centimeters across. It is hardly anything at all. On the other hand, suppose our time traveler had persuaded Queen Isabella that Columbus's geography was faulty, that from Eratosthenes' estimate of the circumference of the Earth, Columbus could never reach Asia. Almost certainly, some other European would have come along within a few decades and sailed west to the New World. Improvements in navigation, the lure of the spice trade, and the competition among rival European powers made the discovery of America around 1,500 more or less inevitable. Of course, there would today be no nation of Columbia, or District of Columbia, or Columbus, Ohio, or Columbia University in the Americas, but the overall course of history might have turned out more or less the same. In order to affect the future profoundly, a time traveler would probably have to intervene in a number of carefully chosen events to change the wheel of history. It is a lovely fantasy to explore those worlds that never were. By visiting them, we could truly understand how history works. History could become an experimental science if an apparently pivotal person had never lived. Plato, say, or Paul, or Peter Grede. How different the world would be. What if the scientific tradition of the ancient Ionian Greeks had survived and flourished? That would have required many of the social forces at the time to have been different, including a prevailing belief that slavery was natural and right. But what if the light dawned in the eastern Mediterranean 2,500 years ago had not flickered off? What if science and experimental method and the dignity of crafts and mechanical arts have been vigorously pursued 2,000 years before the Industrial Revolution? What if the power of this new mode of thought had been more generally appreciated? I sometimes think we might have saved 10 or 20 centuries. Perhaps the contribution of Leonardo would have been made 1,000 years ago, those of Albert Einstein 500 years ago. In such an alternate Earth, Leonardo Einstein would, of course, never have been born. Too many things have been different. In every ejaculation, there are hundreds of millions of sperm cells, only one of which can fertilize an egg and produce a member of a new generation of human beings. But which sperm succeeds in fertilizing an egg must depend on the most minor and insignificant factors, both internal and external. If even little thing had gone differently 2,500 years ago, none of us would be here today. There would be billions of others living on our space, in our place. If the Ionian spirit had won, I think we, a different we, of course, might by now be venturing to the stars. Our first survey ship, the Alpha Centauri, Barnard's star, Sirius, and the Tau Ceti, would have returned long ago. Great fleets of interstellar transports would be under construction in Earth's orbit, unmanned survey ships, liners for immigrants, immense trading ships to plow the sea of space. On these ships there will be symbols and writing. If we look closely, we might see the language was Greek, and perhaps the symbol or the bow of one of the first starships would be dodecahedron, with the inscription Starship Theodorus of the planet Earth. In the timeline in our world, things have gone somewhat more slowly. We are now yet ready for the stars, but perhaps in another century or two, when the solar system is all explored, we will also have put our planet in order. We will have the will and the resources and the technical knowledge to go to the stars. We will have examined how from great distances the diversity of other planetary systems, some very much like our own, and extremely different. We will know which stars to visit. Our machines and our descendants will then skimmed the light years, the children of Ceres and Aristarchus, Leonardo and Einstein. We are not yet certainly how many planetary systems there are, but there seems to be great abundance. In our immediate vicinity, there is not just one, but in a sense 4. Jupiter, Saturn, Uranus each has a satellite system that, in a relative size and spacing to the moons, resembles closely the planets about the Sun. Extrapolation of statistics of double stars, which are greatly disparate in mass, suggests that almost all single stars like the Sun should have planetary companions. We cannot yet directly see the planets in our stars, tiny points of light swamped in the brilliance of solar local suns. But we are becoming able to detect the gravitational influence on an unseen planet on an observed star. Imagine such a star with a large proper motion, moving over decades against the backdrop of more distant constellations, and with a large planet, the mass of Jupiter, say, whose orbital plane is by chance aligned at the right angle, our line of sight, when the dark planet is, from our perspective, to the right of the stars, the star will be pulled little to the right, and conversely, when the planet is to the left. Consequently, the path of the star will be altered, or perturbed, from a straight into a wavy one. The nearest star for which this gravitational perturbation method can be applied is Barnard's star, the nearest single star. Complex interactions of 3 stars in the Alpha Centauri system. Alpha Centauri system would make the search for low-mass companion there very difficult. Even for Barnard's star, the investigation must be painstaking, a search for microscopic displacements of position on the photographic plates exposed at the telescope over a period of decades. 2 such quests have been performed for planets around Barnard's star, and both have been by some criteria successful, implying the presence of 2 or 3 planets of Jovian mass moving in orbit, somewhat closer to their star than Jupiter and Saturn are to the Sun. But unfortunately, the 2 sets of observations seem mutually incompatible. A planetary system around Barnard's star may well have been discovered, but an unambiguous demonstration awaits further study. Other methods of detecting planets around the stars are under development, including one where the obscuring light from the star is artificially occulted with a disk in front of a space telescope, or by using a dark edge of the moon as such a disk, and the reflected light from the planet, no longer hidden by the brightness of nearby star, emerges. In the next few decades, we should have definite answers to which of the 100 nearest stars have large planetary companions. In recent years, infrared observations have revealed a number of likely preplanetary disk-shaped clouds of gas and dust around some of the nearby stars. Meanwhile, some propagative theoretical studies have suggested that planetary systems are galactic commonplace. A set of computer investigations have examined evolution of a flat, condensing disk of gas and dust of the sort that is thought to lead to stars and planets. Small lumps of matter, the first condensations in the disk, are injected at random times into the cloud. The lumps accrete dust particles as they move. When they become sizable, they also gravitationally attract gas, mainly hydrogen, in the cloud when 2 moving lumps will collide. The computer program makes them stick. The process continues until all the gas and the dust has been, in this way, used up. The results depend on the initial conditions, particularly on the distribution of gas and dust density with distance from the center of the cloud, but for a range of plausible initial conditions. Planetary systems, about 10 planets, terrestrials close to the star. Jovians on the exterior, recognizably like ours, are generated. Under other circumstances, there are no planets. Just a smattering of asteroids, or there may be Jovian planets near the star, or Jovian planet may accrete so much gas and dust as to become a star, the origin of a binary star system. It is still too early to be sure, but it seems that splendid variety of planetary systems is to be found throughout the galaxy, and with high frequency. All stars must come, we think, from such clouds of gas and dust. There may be 100 billion planetary systems in the galaxy awaiting exploration. Not one of those worlds will be identical to Earth. Few will be hospitable. Most will appear hostile. Many will be achingly beautiful. In some worlds, there will be many suns in the daytime, many moons in the heavens at night, or great particle ring systems soaring from horizon to horizon. Some moons will be so close that their planet will loom high in the heavens, covering half the sky. And some worlds will look out onto the vast gaseous nebula, the remains of an ordinary star that once was and is no longer. And all those skies, rich in distant and exotic constellations, there will be a faint yellow star, perhaps barely seen by the naked eye, perhaps visible only through the telescope, the home star of the fleet of interstellar transporters exploring this tiny region of the great Milky Way galaxy. The themes of space and time are, as we have seen, intertwined. Worlds and stars, like people, are born, live and die. Lifetime of a human being is measured in decades. The lifetime of the sun is 100 million times longer. Compared to a star, we are like mayflies, fleeting, ephemeral creatures who lived out their whole lives in the course of a single day. From the point of view of a mayfly, human beings are stolid, boring, almost entirely immovable, offering hardly a hint that they ever do anything. From the point of view of a star, human beings are tiny, flash, one of billions of brief lives flickering tenuously on the surface of a strange cold, anomalously solid, exotically remote sphere of silicate and iron. In all those other worlds in space, there are events in progress, occurrences that will determine their future. In our small planet, this moment in history is historical branch point, as profound as the confrontation of the Ionian scientists with the mystics 2,500 years ago. What we do with our world in this time will propagate down through the centuries, and powerfully determine destiny of our descendants and their fate, if any, among the stars.